Similarly, if you have a light beam that's weak enough, going over by single photons worth of energy one at a time with a double slit experiment, you actually see the exact same thing. You can only observe one photon worth of light energy at a time, so it comes up as little bleeps one after another. It's only when you build up a whole range of them, just like in the electron experiment, that you see this overall pattern. So this led to the following interpretation, so-called the Copenhagen interpretation, because that's where the conference was held. The waves then becomes associated with a probability of detection at that point. If you have a big amplitude of the wave there, that means it's more likely for you to be able to absorb or detect that particle. And so it becomes this kind of weird notion that's basically at the crux of the wave-particle duality, that particles and light, everything, propagates and move like waves, in the sense that there's probability of detection over a large range of space. But then when it comes time to detect it, they exhibit the particle behavior where you just get one bleep at a particular point. And where it actually ends up, it's completely random and statistical, as far as we know. Years and years of trying to search for something a little more meaningful has not produced anything. Apparently nature is this weird statistical beast that we have to deal with. But due to certain mathematical relationship, it turns out that the wave function, so to speak, doesn't give probability directly, but similar to how light, you can't add up the power of two rays to give the overall power of the wave because of interference. The wave is first of all represented by the electric field amplitude, and the electric field amplitude square is what gives you the intensity, the power, which is what you observe, which allows for interference before mixing it all up together. Similarly, the probability of detecting a certain particle at XYZ at that time is directly proportional to the magnitude of the wave function square. Of course, this also depends on XYZ and time. Now, I put these absolute value sign there because once the math works out, it turns out that this wave function is inherently complex, so we have to do the wave function times its complex conjugate. And Schrodinger was the first person to kind of write down a wave equation for such these matter waves, which is of course called Schrodinger's equation. Now, I'm probably completely butchering the pronunciation of Schrodinger. Stick it into Google Translate if you want the proper pronunciation, and we'll just go on with the math. So at this point, what do we know about the matter wave? Well, we know that from De Broglie's work, we can write the energy of the particles related to its frequency. And just for symmetry's sake, we often like to write that, where h bar is equal to h over 2 pi. And also, the momentum is related to the wavelength, which allows us to write this, k being the wave number. And so you can kind of see where we're driving at, because once again, we're going to start from what we expect to be the answer and see what kind of behavior it plays with. Our go-to solution is once again the plane wave. We're going to stick with 1D for now, so it's in xn and t. Therefore, we have some amplitude e to the I, basically kx minus omega t. So to write it like that, I have px minus et dividing out the h bar. This would tend to describe a particle that's traveling freely in space. So when you have a plane wave traveling in a certain direction in empty space, basically, that kind of hints at this would represent a particle traveling freely without any potentials around it. So let's jiggle this around until we get something that looks like a wave equation. First off, we're going to take the time derivative. We get negative I over h h bar, the E comes down, of the same exponential. If we take the space derivative, you get the IH bar times P coming down with the same exponential mess. Okay, so then we need some way to relate these two relationships, and for a non-relativistic particle, we know that the energy, in this case once again, because we don't have any potential around, the particle is just moving freely, E equals 1/2 mv squared, and P is equal to m times v, so we can make this relationship P squared over 2m. So in order to get a P squared, because if we sub this in we get a P squared, we need to derive this again. So di square square, we get negative 1 over h bar square P square, and this up here we rewrite as di t psi is equal to negative I h bar P squared over 2m psi. Now, solving for P squared psi and equating both sides, we end up with this lovely equation, which relates our spatial derivative with our temporal derivative. However, something is amiss here. First off, you have a double spatial derivative, but a single temporal derivative. And there's a complex factor of I out here. Well, h bar is real, m is real, but there's an h bar out here. Both of these, because it's a single and I, so the solution actually has to be inherently complex. No more of this real operator, looking at a cosine, no more. And that's why when we deal with working out the probability, we can't just take the square of the function, we have to take itself times the conjugate. And when you do that, just want to quickly point out that any phase shift in the wave, because we're doing the amplitude that matters, the phase shift actually don't have very much observable effects. And this brings us to a close to our story, as we have come all the way to the Schrodinger equation, which describes these matter waves for a 1D free particle. There's one little additional step when we have potential energy involved, but this is basically how we've come about and made these matter waves, and starting with this wave mechanics and evolving into quantum mechanics as we know it.